Let us see now how the concept of virtual ground works. So we said that the output will float to some value that ensures that both the input terminals have the same voltage. Since terminal 2 is fixed to ground, and if both terminals have to have the same voltage, that means essentially terminal 1 also goes to ground. Okay, so this is the concept of virtual ground. Physically, it is not connected to any ground terminal, but the potential at this point will float to the same value as the potential at this point. So terminal 1 will also be equivalent of ground. Now, if you want to let me just get this. Yeah, so now if you want to solve the system to find out what is the output in terms of the input, then essentially the equation you have to do is, since the terminal 1 is like a virtual ground, there is some current I1 flowing into the terminal. So what is I1 equal to? I1 is the input voltage Vi minus ground 0 by R1. Now we know that the inputs draw no current. That means the current I1 which is flowing into this virtual ground cannot flow into the op amp, and current continuity has to be maintained. That means the same I1 is actually flowing over here and then going to the output side. Okay. So what is the current flowing to the output side? That's equal to 0 minus V0 by R2, right? It's the same I1 current. So here it is Vi minus 0 by R1, and the same thing is equal to 0 minus V out by R2. So what is the value of V0 or the V output is equal to minus R2 over R1 into Vi. So this is why it's called the inverted configuration, because the output voltage is the negative of the input voltage. And what is the value of the gain? It's R2 over R1. So this is following the same op amp equation. And if R2 were equal to R1, then V0 will be equal to minus Vi. That means it's a unity gain system, but it's the inverted version of the input. So this is the inverted configuration. What would you do for the non-inverted configuration? Now, if you follow the same principle, here we called it virtual ground because terminal 2 was connected to ground, so 1 has to go to ground. Here, the positive terminal is connected to the input voltage. So this point, let's call it as Vx. Vx has to be equal to Vi. Okay, so this is all for this case. And now let's start the next exercise. So Vx is going to be equal to Vi. And since this is at a value Vx and it's connected to ground, so current has to flow. So there is a current I. What is the current I going to be? I is equal to Vx by R1. And as we know that no current can flow into the op amp, so the same current is given by V0 minus Vx over R2 because of current continuity. So the same current is flowing here as well. And what is the value of the output now? This implies V0 is Vx into, so V0 by R2 is Vx into 1 over R1 plus 1 over R2 implies V0 is Vx into 1 plus R2 over R. So this is the gain, okay? And this is the input voltage Vx, because Vx is nothing but Vi, right? So I can just replace this as Vi. So the output is Vi into 1 plus R2 by R1. This gain and the gain in the previous case, these are all called closed loop gain. Closed loop gain. This is also closed loop. This is the closed loop gain of the inverted configuration. This is the closed loop gain of the non-inverted configuration. What we saw in the previous slide was the gain of the comparator. That's the open loop gain. Okay, so this is open loop gain. So generally the open loop gain, according to point number 4, is infinite. That means it's a very large number. But the moment you put feedback, then the gain of the system becomes much smaller, and that is given by the ratio of the resistances. Note that the gain over here no longer depends on the open loop gain of the system. It's dependent by the external biasing resistors over here. So there is similarly the other configuration, which is the difference amplifier. We saw in the case of the comparator that the characteristic looked like this, where this is the ideal comparator. So this is the V out. So in the ideal case, if the V2, if delta V is V2 minus V1 is plotted over here, this is delta V, and delta V is given by this, then what we can say is if delta V is positive, the output is some positive constant number. If delta V is negative, the output is some constant negative number. But I want to have an amplifying system, which means that the output should follow the input with gain. So I want something which looks like this. I don't want the step function. So the step function is like a digitization. It's like making the system binary. It's either -1 or +1. But I want something which is a analog system, which is a amplifier. So to do that, this is the configuration, and you will notice that this is a combination of the inverting and the non-inverting. Okay, so let's see what the values are going to be like. So the voltage at this point is going to be Vi2 into R4 over R3 plus R4 using simple voltage divider circuit, right? So this is the voltage at this point, and this is fixed. Now, due to the principle of the inputs having to reach the same value using the negative feedback, so this voltage will have to reflect here as well. Okay, so let's call this as Vx, right? And Vx is equal to this value. Now, if I want to write the equation, then what do I have to say? Vi2 minus Vx over R1, that's the current flowing in, is going to be equal to Vx minus V out by R2, right? So what is the value of the output voltage? It's going to be Vi2 by R1 into R2 by R1 plus okay, the signs, so since VO goes to the other side, so this is actually minus over here, and this will become plus R2 by R1 plus 1 into Vx. So let's see if you're able to get this. Now, if you want to substitute the value of Vx into this equation, then essentially the output voltage V out is R2 by R1, 1 plus R2 over R1 into Vx is R4 over R3 plus R4 times Vi2 minus R2 over R1 times Vi2. So I think that's a mistake on the top. The first one should have been Vi1 minus Vx over here, because that is Vi1 minus Vx. So that was, let's just change those 2's to 1's. It's Vi1, and same here. It should be Vi1 and this is Vi1. Oh no, sorry. So this is 2, this is 1. So now you can rewrite this equation as 1 plus R2 over R1 times 1 by 1 plus R3 over R4 Vi2 minus R2 over R1 Vi1. Now if I want this to be a difference amplifier, then essentially what I want is V0 should be equal to some constant times V2 minus V1. So in this circuit, what can I do? If I make the ratio of R2 by R1 equal to R3 over R4, then these two will cancel out. And if I make R2 over R2 equal to R1, then essentially what I can get is V0 is equal to Vi2 minus Vi1. So this is like a difference amplifier. It's exactly telling you what is the difference between the two inputs. Now, one of the metrics of a difference amplifier, and this is something you should know because in the outside world, this is a question you'll always get. What is the common mode rejection ratio? And what that means is how well is the op amp able to reject signals which are equal to each other? Because we know that the op amp should only amplify, the output should be like some amplification times V2 minus V1, right? So if there are any common values, those have to be rejected. So how do you think about that? Let's say that I have this, x-axis and y-axis. Let's say that this is the value of V2 and this is the value of V1. Then if I take the average of V1 and V2, that will be some value in the middle. Okay, so this is like average of V2 and V1. And the average means it's midway between V2 and V1. So I can represent the signals V2 and V1 as some average value plus some difference and average value minus some difference, right? And that's what is shown over here. So the average value is called the common mode, the common of the two things. And then there is a differential value. So the input, which is written as Vi1 and Vi2, can be replaced by the average of Vi1 and Vi2. So Vi1 plus Vi2 by 2, that's called the common mode signal. And the differential signal is Vi2 minus Vi1. The difference is Vi2 minus Vi1. And half the difference is adding to the common mode signal to give V2, and half the difference is subtracted from the common signal to give V1. So that's what is shown here. So Vi1 is the common mode, which is the average value, minus some difference, and Vi2 is the common value plus some of the difference. And the common mode rejection ratio then is given by the metric which is here, 20 log AD by ACM. Okay, so this is the differential mode gain and the common mode gain. That means the output can be written as, so if I use this system, then I can write the output as some differential gain into the differential signal AD into VD plus the common mode gain into the common mode signal VICM. So you can work this out as an exercise to see that how I can write the output as the, I can rewrite the output in terms of the differential and the common mode signals, and the ratio of the differential mode and the common mode gain, that's called the common mode rejection ratio. That means how well am I able to reject the common mode signal. Now there are other applications. So we talked about the inverting configuration with a resistor was amplifier, inverting amplifier. And now if I replace this resistor with a capacitor, then what happens? So in the case of the resistor, I'll just write it. If this was the resistor, then we had the equation that V0 was minus RF over R1, R2. Let's call it as the resistor was R2. So R2 by R1 into Vn. Now I have a capacitor. So what happens to this case? So if you were to follow the same procedure as before, the current I1 is given by I1 is V1 minus 0 because of the virtual ground over here. So this is also a virtual ground. So V1 minus 0 by R is the current flowing in. And what is the current flowing at the output across the capacitor? The current is C dV by dt. Okay, so that is C times d by dt of the voltage across the capacitor. What is the voltage across the capacitor? C of 0 minus V naught, right? Because the current is flowing out here. So if I want to now write the output in terms of the input, then what do I get? This implies V naught is equal to minus 1 over RC integral Vi dt. Okay. Plus, since it's an integral, there might be like some initial constant. So let's say some voltage across capacitor. That means this is actually an integrator system. So when the input is, whatever input voltage you have, that is getting integrated across the capacitor, and the output is showing the integration of the input. So that's like a cool function, right? So what if you wanted to use a differentiator now? How would you do that? So in the meanwhile, let me write the output here. So this is V naught is minus 1 over RC. The negative is coming because of the inverting configuration, integral Vi dt plus, so actually since we could probably call it as a minus Vc because there is a minus sign. So by convention, we normally say it's integral of something plus constant. So the minus will apply to the constant and become minus Vc. So now how do I get a differentiator? So the simple way is you can swap the capacitor and the resistor. So if I were to put the capacitor here, let's say the capacitor comes here and the resistor comes here, then what will happen? These equations will just change. That means it will become, let's see if I can change the color, that will make things easier. So in this case, the capacitor is here and the resistor is here. So if I want to work this out, then what will happen is the current flowing into the system is now I1 is C times dV1 by dt is going to be equal to the current flowing out is 0 minus V0 by R. I mean, you have to visualize. I have swapped the capacitor and the resistor, and that implies the output V0 is minus RC dVi by dt. Let me call this as Vi or V1. Just keep it consistent. So in this case, it becomes a differentiator because the output is the dV is proportional to dVi by dt. Now the same thing by principle of duality, instead of this, we could have also proceeded the original way. Let's say I had the same op-amp circuit, the minus plus. We could potentially have used an inductor over here in place of the capacitor. And we know that in general, the capacitor and inductor are like dual elements. So if I had the same circuit over here, and if I had a capacitor, it became an integrator. If I were to put an inductor, it would have become a differentiator. So just remember that. I mean, that's something you can work out as an exercise. The equation of the inductor is nothing but the voltage is L di by dt. So you can just plug it. In the case of a capacitor, it was the current was C dV by dt. In the case of the inductor, the voltage is L di by dt. So you can see the duality of it. So in the same circuit, if I replace the capacitor with a resistor, I get the minus R2 by R1 Vn. If I were to put a capacitor, then it becomes a integrator. If I were to put an inductor, then it will become a differentiator. Okay. So this is something you can try out. I had given as an assignment last time to deduce the functionality of this circuit. So let's do that as one last example so that we are completely confident about how this works. So this is again inverting configuration, closed loop, and the positive terminal is at ground. So there is a virtual ground over here. The current flowing into the system is I1 is V1 over R And this is the same current. Since it cannot flow into the op amp, it has to flow through the diode. So this is now equal to the diode current. Okay. So it started off flowing into the resistor and now it's flowing into the diode, and that's equal to ID. And what is the value of ID? We know from the formula that it's exponential of VD, some voltage drop across the diode. So let's say there's a voltage drop across the diode over VT, which is the thermal voltage, minus 1 into some I naught, right? I naught is the reverse saturation current. So I can write this as V1 over R times I naught is equal to, and I can just put the I naught here as well, V1 over R I naught one is equal to exponential of Vt over Vt. Okay? And that implies, and the I naught is a small number, it's the reverse saturation current of a diode. Since I naught is a small number, you can assume maybe that we can cancel away the 1 and make life easy, because if this is a small denominator, then this is a large number, and so you can neglect 1, and therefore the value will become Vd is equal to Vt log V1 over Ri naught. Okay, but remember what we're trying to get is the output voltage. And what is the output voltage? We said that the current flowing through the diode is given by the drop across the diode. One side is fixed at ground and one side is VO. So that means VD is equal to what? 0 minus VO, right? So VD is nothing but minus VO. So the output voltage and VD is equal to minus VO. So the output voltage is minus Vt log V1 by Ri naught. Okay. And the denominator is a constant, Ri naught. So that means essentially what we are saying is the output voltage is minus log of, is proportional to, the output is proportional to the negative log of the input. Right. So this is called a logarithmic amplifier. So we've seen various kinds of circuits now, right? We saw the inverted configuration, which was an inverting amplifier with a certain closed loop gain. And then we saw the non-inverting configuration, which had, so it's non-inverting, that means there is no minus sign here. The inverting configuration always gets a minus sign. So the inverting configuration had minus R2 by R1, the non-inverting had 1 plus R2 by R1. By combining the inverting and the non-inverting, we got a difference amplifier, so that the output is directly proportional to Vi2 minus Vi1. Then we went ahead with the same inverting configuration and replaced the resistor with the capacitor and found that the circuit becomes an integrator. If I replace the capacitor with the inductor, then the circuit becomes a differentiator. And if I don't want to use an inductor in the circuit, I can swap the capacitor and the resistor. So the capacitor goes here and the resistor comes here, right? So this capacitor is C and this is R. So if I swap these, then also I can get a differentiator. And finally, what we saw was if I use some other nonlinear element like a diode, then essentially I can get a logarithmic amplifier. So these are all different functionalities of the op amp. Finally, we talked about the precision rectifier last time. And I'm just going through these things more slowly and in detail so that whatever various doubts you had becomes clear if we go through the mathematical working of it. When you consider the normal diode rectifier that we studied in the past, let me remind you. So this was a diode, and then there was a resistor, and there was the input voltage given here, and then we measured the output. So the way this curve would work is if you have the input voltage, which goes this way, then the output would take only the positive cycle, because during the positive cycle the diode conducts, during the negative cycle the diode is reverse bias. So if this is the Vi and this is V out, then what we can say is that in the negative cycle, the diode will not conduct. And in the positive cycle, what will happen? The diode conducts, but there is a small drop across the diode. So the output goes something like this. I'm drawing it in a little exaggerated fashion, where this difference between the output and input is like approximately 0.7 volts, right? So the input would have been looking something like this. And we saw that the diode is not able to, loses about 0.7 volts in the precision rectifier. Now, supposing I have applications where I want to rectify a sinusoidal voltage whose value itself is 100 millivolts. 0.7 volts is equal to 700 millivolts, right? So my regular diode is losing 700 millivolts, and now I want to amplify something which is 100 millivolts. It's not possible, because if I apply a 100 millivolt signal over here, the diode is practically always reverse biased. Even in the forward bias, you cannot cross cut in, and in the reverse bias, it's reverse bias. So you'll never get any output. So for the sake of precision rectification, this is called a precision rectifier. What we do is we use the op amp to make a circuit like this. And the way you can understand this is, supposing, so this is again in the non-inverting configuration because the output is connected to the negative terminal. And this is a negative feedback, sorry, not non-inverting. This is a negative feedback configuration because the output is connected to the negative terminal and the input is applied to the positive terminal, okay? And the output is measured. So VA is not the output is V naught. VA is this whole dashed line box is like the whole circuit. VA is like an internal quantity. It's the output of the op amp, but it's not the output of the circuit. The output of the circuit is V0, okay? And that's what you're measuring over here. V0 is measured across the load resistance. So when the input is positive, okay? So when the input is a positive number, then the output becomes a positive value because the output is V positive minus V negative. And since the output is a large positive number, the diode becomes forward biased and this path can conduct, the feedback path can conduct. If the input is a negative value, right? So let's say initially the circuit is off. If the circuit is turned off, then what happens? The only source of voltage is the ground over here. That means the negative terminal is connected to ground. And now I've turned on the circuit. So initially this voltage is 0 because it's connected to ground. Now what's happening is, if supposing I give a negative value at the Vi, then the negative value over here, the output will be some negative value minus ground, which is a completely negative value. And since the output is negative, this diode will become reverse bias because 0 is like at the positive edge and negative value at the negative edge. So this is reverse bias. And what will the output be? The output will be 0. So VO. Why is the output 0? VO? Because VO is also connected to ground. So let me again, discuss this carefully. I'll use a different color. So let's go back to the earlier one. So I have the input. Is doing the cycle. And then I'm trying to capture the output. So when the input is a negative value, then what happens? The VA, let's say when VI is, let's write it over here. So when VI is negative, then what happens? VA is some gain times Vi minus 0, which is negative, right? And if VA is negative, then this diode is reverse bias. If the diode is reverse bias, this path is broken. If this path is broken, then what happens? VO is connected to ground and this negative side is also connected to ground. So nothing happens. Basically, there is no feedback path and the system goes to 0. The 0 because VO is connected to ground. Now let's consider the case when Vi is positive. When Vi is greater than 0, then what happens? Va becomes a positive number as given over here. So Va is equal to Vi minus Vo, because the value that you're seeing here is Vo, right? Vo is connected to this point and Vo is also connected to ground. So let's assume there was some value of Vo. So this is a general equation. In general, Va is equal to some gain of the op amp times Vi minus Vo, because Vo is the point which is connected over here. And we also know that Vo plus 0.7 volts is equal to Va. Why is that? Because if Vo is the value, if the diode is on, then there is a drop of 0.7 volts across the diode. So when the Va is a positive number, like let's say it's 10 volts, then what will happen is the diode will take 0.7 volts to turn on, and the moment the diode is on, the rest of the voltage will drop here. So this, if Va is equal to 10, then this will be like 9.3, right? And that's what the output will see. And this region will be 9.3 volts, and then there will be a current flowing here, which will be like 9.3 volts divided by RL would be the I, right? So that much current will flow into this path. So when the system is positive, the VA is in the positive voltage, then this relationship will hold. It generally holds. So V0 plus 0.7, V0 is 9.3 plus 0.7 is equal to 10. That's equal to VA. Okay. So now let me just erase this. So if I were to solve these two equations simultaneously for the positive side of the diode, then we said that Vi minus V0, Vi minus V0, which is connected over here, times A is equal to Va. So if I were to, rewrite this equation, I'm bringing Va on the other side. And then I'm saying that Va is equal to V0 plus 0.7. So that's getting substituted here. So this goes into this and it becomes this. And then if you were to solve this equation, you can say that V0 is equal to AVI plus 0.7 minus 0.7 over 1 plus A. What is the value of A? Like we said, A can be like about 1 million because A is a very large number. A is what? Open loop gain. Okay. A is the open loop gain. So as A is a very large number, then A over 1 over A is equal to what? It's 1 million over 1 million plus 1. So that's equal to 1, right? Because compared to 1 million, 1 is a very small number. And what happens to the other number, 0.7? So 0.7 divided by 1 million is also approximately equal to 0. So that means this term tends to 0 and this A over 1 plus A tends to 1. That means the V0 is equal to Vi, right? So this is a precision rectifier. This relationship holds for what? The positive side. So when I have the positive signal, V0 is equal to Vi. In the negative side, 0. Again this. And here you are not going to see the 0.7 volts drop. Okay. The point is the very large gain of the op amp ensures that through this feedback system, you can overcome the loss due to the diode. So the diode is the rectifier. It's the same as the earlier one. Look at this. So there is the same diode over here. And then this is the load resistance RL. You are measuring V0 across RL. So it's the same circuit as before. The only thing is these two terminals had an op amp connected over here in between. Okay, so there's an op amp connected over here in between, and that's ensuring that the drop across the diode is minimized by the gain of the op amp. So let's just clear some of this clutter and let's remove all this. And this figure corresponds to this, and this figure corresponds to this. Okay, and I think that's about it. So that's basically the precision rectifier. And I know it might be getting a little intense, but if you do a lot of these, exercises by hand, then it will, help you get a good understanding of the op-amp. And, you'll have the lab coming up and you'll have more fun in the lab when you know how to, manipulate these various quantities. So the final thing is a positive feedback system. Remember that all this while, all the circuits we dealt with was negative feedback. That means the output was connecting to the negative terminal. Now what is happening is the output is going to the positive terminal. So this is the first time we are seeing something like this. Okay, so this is a positive feedback system. And in positive feedback, those golden rules don't hold. In the negative feedback, what happened was when you had the output going to the negative terminal, going back to the negative terminal, the output would always reduce the input difference and ensure that the two inputs V1 and V2 came close to each other. Now what's happening is this is gone and this has become a positive feedback path. That means if I have, say, I call this as V2 and this is Vn, then the output is some gain times V2 minus Vn. And if V2 is bigger than Vn, then the output is a large positive number. And now a positive number is going back. So in the next time step, V2 has now become like, V2 plus V out. So now this is like a positive reinforcement. It's increasing the distance between V2 and Vi. Earlier, the negative feedback reduced the gap between V2 and Vi and made them almost equal to each other. Hence, we could use the concept of virtual ground. Now you cannot use virtual ground, right? So no virtual ground. And no golden rules, because the golden rules applied for negative feedback, whereas this is under positive feedback. Now, of course, one of the rules still holds, which is current does not flow into the op-amp. That is because the op-amp has infinite input impedance. Okay, so let's get this going then. So let's see how the Schmidt trigger will work. There is something called hysteresis that happens here, and I'll explain to you what it means shortly. Let us consider the case that R1 equal to R2, okay? And that means what is the value of V2? V2 is equal to V out divided by 2, right? If R1 equal to R2, this is a resistor divider network. On one side I have V out, on the other side I have ground. So V2 is equal to V out divided by 2. Now, supposing I have an input signal, which is Vn, going into the system, let's call this Vn. Then what's going to happen to V out? If the Vn is a positive number, then the Vn is going to the negative terminal. So the output is some value minus a negative value, right? So V out, like as we have here in this equation, we've said that V out is A times V2 minus Vn. And if Vn is a negative number, then minus of minus becomes plus. So this becomes a positive number. So the V out goes to a positive number, and that positive feedback goes to V2 as V out by 2. And because this is a positive number and this is also, the negative of a negative, so this whole thing goes to a positive saturation. So when the input is actually when the input is negative, so I should say over here, since I've started with positive input, so maybe let me do this. Okay, and let's scratch out this part. So let's say the system is starting from here. So the input is starting from negative, and what we said is the output goes to some positive saturation value. Okay, so this is like VCC, and let's call the negative region as minus VEE. These are the power supply values. So when the input goes negative, then we said that negative of minus V will become like a positive number. And therefore this whole quantity becomes positive V out, and then it goes to a positive saturation value. So it stays at saturation. Now what happens when the input goes to 0? When the input is 0, condition Vn is 0, the output is already positive, right? So V2 is equal to what? It's like VCC divided by 2, right? Because we said V out goes to saturation at VCC in the previous case, and V2 is V out divided by 2, assuming R2 is equal to R1, this condition. So the V2 is VCC divided by 2. When the input goes to 0, what is the value of V out? It is A times V2 minus Vn. Vn is 0, V2 is VCC by 2, so V out is still positive. So although the input goes to 0, the output still remains positive. What if the input starts becoming positive now? Okay, so the input starts becoming positive. So Vn is now slightly greater than 0. Okay, it's slightly greater than 0. Now what happens? Let's say V2 is VCC by 2, and if VCC was like about 5 volts, then this would be like 5 by 2 is like about 2.5 volts, right? And supposing the input voltage is like say greater than 0, so let's say it's approximately equal to 0.5 volts. We are just going with some rough numbers to understand how the system is working. So if the input is like 0.5 volts, then what is the value of V out? V out is A into V2 minus Vn. V2 is like about 2.5 volts. Vn is like 0.5 volts. So this is still positive number, right? Because it is 2.5 minus 0.5. And so the V out is still a positive number. That means when the input is going positive, the output has not changed its sign. When will the output change? We said that, let's say the input goes from, let's say the input goes from plus 5 to minus 5 volts. Then if V2 is like VCC divided by 2.5 volts, if you want to cross this number, then the input has to cross 2.5 volts. Okay, so think about this little carefully. So when you cross 2.5 volts, so this is like about 2.5 volts at the input, then the output goes and switches to negative. And then the output stays negative, and then let's say the input does this and goes back. What will happen is when the output will stay negative until the input goes to minus 2.5 volts, and then again it will kind of switch back, right? So the point is that this system is also like a square wave generator, but the square wave is not generated at the zero crossing point, it's at some finite crossing point. If you had the basic comparator, let's say I had the basic comparator, and this is V out, and there is the positive and negative terminal, and let's assume that the positive terminal is grounded, and then I'm giving the input to the negative terminal Vn. Then here what would happen if I had an input voltage which goes like this, and since the input is given to the negative terminal, the output will basically go to a value which looks like this. This was the basic comparator, right? But it is out of phase with the input because the input is given to the negative terminal. So the basic comparator means if one terminal is grounded, then whatever is the input, the output will go to the opposite value and the crossing will happen at 0. In the case of this Schmitt trigger, which is this circuit, the Schmitt trigger, when the output is, the output is basically following the input with some lag. So it does not follow the 0 crossing point, but it has to, cross a certain threshold before it can switch. So this is something you have to understand carefully, and this is called a hysteresis. That means when the input is going in one direction, it has to cross a certain threshold before the output will switch. Once the output has switched, again the input has to go to the negative side by a certain threshold before the output switches back. So let me use a different color again. So this is the input. So when the input is negative, the output is negative, but then the input has to cross some threshold before the output can switch. But then when the input is again going back to negative, the output will not, switch back over here. This does not happen. It has to go to a certain threshold before it can switch back. So this is basically called hysteresis curve. Okay? So this is how the Schmidt trigger works. And there was I think exercise given, or here is an exercise that you can try out. If I have a certain biasing configuration, what is going to be the switching points of the output? For what input values is the output going to switch? So overall, the summary is that we learned that the op-amp is an open loop system. It can be used as a comparator. Once you apply feedback and negative feedback, then you have golden rules, which means that you can use this concept of virtual ground, and the two inputs will always float to the same voltage. If you have positive feedback like the Schmidt trigger, then the golden rules will not hold. And in the positive feedback, the output still behaves as a comparator. That is, it's either VCC or VE, right? So that's what is shown over here. The positive feedback, Schmidt trigger, is still a comparator, but it's different from the open loop comparator. In the open loop comparator, the crossing happens at 0. In the Schmidt trigger kind of comparator, the crossing happens at some value greater than 0. So when you're going in the positive side, you have to exceed 0 by some value. Then when you're going in the negative side, you have to go below 0 by some value, right? So it has certain trigger points. So let's stop here, because I think this is again become another intense class. But if you have any questions, then please feel free to email me or post it on Moodle. Thank you.